What if everything we thought we knew about the infant universe was wrong? Imagine standing in a delivery room watching a newborn take its first breath. Now imagine that newborn opening its eyes and reciting Shakespeare. That this tiny, fresh life already possessed the complexity, the sophistication, the sheer brilliance of something that should have taken decades to develop. You'd question everything you understood about human development, wouldn't you? That's precisely the position astronomers find themselves in right now. Because deep in the cosmic abyss, nearly 13 billion light-years away, the James Webb Space Telescope has discovered something that shouldn't exist. A galaxy so luminous, so intricate, so impossibly advanced for its age that it's forcing us to rewrite the story of cosmic evolution itself. This isn't just bright. We're talking about a galaxy that outshines nearly everything we've observed from that era of the universe, a time when the cosmos was barely 400 million years old. A cosmic infant that somehow built cathedrals instead of sandcastles. The discovery carries a weight that extends far beyond a single anomaly. It whispers of possibilities we hadn't dared consider, that the early universe wasn't the simple, chaotic nursery we imagined, but something far stranger, far more capable. And tonight, we're going to journey back to the edge of time itself to understand what this brilliant, ancient galaxy is telling us about the universe's hidden potential. To understand why this discovery is so profoundly unsettling, we need to travel backward through time. Not just years or centuries, but billions of years, to an epoch so remote that the universe itself was unrecognizable. Picture the universe roughly 400 million years after the Big Bang. In cosmic terms, this is infancy. To put it in perspective, if the universe's current age were compressed into a single year, we're talking about January 2nd. The celebration confetti has barely settled. At this point in cosmic history, the universe had just emerged from what astronomers poetically call the Dark Ages. Not dark in the emotional sense, but literally, a period when the universe contained no stars, no galaxies, nothing to generate light. Just vast clouds of primordial hydrogen and helium drifting through the expanding void, cooled from the Big Bang's initial fury into a cold, lightless fog. The physics of this era painted a very specific picture of what should happen next. Gravity would slowly, patiently gather this gas into clumps. Small irregularities, quantum fluctuations frozen into the fabric of space during the Big Bang's first fractions of a second, would serve as seeds. Dark matter, invisible but gravitationally present, would provide the scaffolding. But this process should have been gradual, agonizingly slow. The first stars were expected to be solitary and massive, living fast and dying young in spectacular supernovae. Only then could their deaths seed the formation of subsequent generations. Each cycle would build upon the last, gradually increasing in complexity. The first galaxies, by all reasonable models, should have been small, dim, and primitive. Think of them as cosmic villages, modest collections of early stars, irregularly shaped, lacking the grand spiral arms or elliptical perfection of mature galaxies like our own Milky Way. They were supposed to be the universe's rough draft, the prototype versions that would eventually merge and evolve into the majestic structures we observe in the modern cosmos. The timeline for developing truly complex, luminous galaxies was measured in billions of years, not millions. It's a process that requires patience, countless stellar generations, and the gradual accumulation of heavier elements forged in stellar furnaces and scattered by dying stars. This wasn't speculation. This was our best understanding, built on decades of observations, simulations, and fundamental physics. The Hubble Space Telescope had glimpsed some of these early galaxies, small, faint, and exactly as predicted. Everything made sense. The universe was following a comprehensible narrative from simplicity to complexity, from darkness to light. And then James Webb opened its infrared eyes and saw something impossible. The James Webb Space Telescope isn't just an improvement over Hubble. It's a revelation machine, specifically designed to peer deeper into the universe's past than ever before. Its massive golden mirror, composed of 18 hexagonal segments, collects infrared light, the stretched, reddened wavelengths from the most distant objects, their light exhausted from traversing billions of light years of expanding space. When Webb turned its gaze toward a seemingly empty patch of sky, conducting what astronomers call a deep field survey, it was searching for these faint whispers from the early universe. What it found was a scream. The galaxy, catalogued with the clinical designation that belies its extraordinary nature, blazed across the detector, not with the timid glow of a cosmic newborn, but with a brilliance that immediately sent shock waves through the astronomical community. Its luminosity exceeded predictions by orders of magnitude. We're talking about a galaxy shining with the collective light of billions upon billions of stars. But brightness alone, while startling, wasn't the most disturbing aspect. It was the structure. Modern galaxies are complex machines. They have defined morphologies, spiral arms tracing density waves, bulging cores dense with ancient stars, halos of dark matter, regions of active star formation glowing in the ultraviolet, and quiet neighborhoods where stellar birth has long since ceased. This complexity is supposed to be earned through billions of years of evolution, mergers with other galaxies, and countless cycles of star birth and death. The spectrum of light from this ancient galaxy told a story that shouldn't have been possible. Multiple stellar populations were present, not just one generation of primitive stars, but several, each with distinct chemical signatures. This implied that multiple cycles of stellar birth, life, and death had already occurred. Stars had formed, lived their entire lives, exploded, and seeded new generations with heavier elements, all within the first few 100 million years. The galaxy showed signs of organized structure, not the chaotic, irregular blob expected from this era, but something approaching the complexity of galaxies billions of years older. Regions of intense star formation coexisted with areas containing older stellar populations. The distribution of matter suggested gravitational sophistication, as if the galaxy had already undergone significant evolution. Most puzzling of all was the sheer mass. This galaxy contained matter equivalent to billions of solar masses. The star formation rate necessary to accumulate this much stellar mass in such a short time bordered on the physically extreme. We're talking about a galaxy that would need to be forming stars at a rate hundreds of times faster than our own Milky Way currently manages. Think about what this means. The universe at 400 million years old is still incredibly young, incredibly hot, and incredibly turbulent. The cosmic microwave background, the afterglow of the Big Bang, still permeates space with significant energy. The conditions aren't exactly hospitable for the kind of stable, efficient star formation we observe in the modern universe. Yet somehow, this galaxy managed to not just form, but to thrive, to shine, to build complexity at a pace that our models suggested should be impossible. Astronomers reviewing the data experienced a peculiar mix of excitement and dread, the kind you feel when your fundamental assumptions are being challenged. Because if this galaxy exists, if it's real and not some extraordinary observational artifact, then something is deeply wrong with our understanding, or perhaps more accurately, something is missing from our story of how the universe grew up. The discovery of this brilliant ancient galaxy doesn't just add a new data point to our cosmic census. It demands a fundamental rethinking of early universe physics. Consider the problem of time. Star formation, even under ideal conditions, takes time. A massive star lives for just a few million years before exploding in a supernova. Smaller stars live longer, but contribute less to the overall luminosity. To build a galaxy of this brightness and complexity, you need multiple generations of stars, each taking millions of years to form, live, and die. But the universe at this epoch is only 400 million years old. That's the entire available time frame from the moment the first stars could form until this galaxy's light began its journey to us. It's like asking someone to build a skyscraper between breakfast and lunch. Theoretically possible if you could somehow work impossibly fast, but it requires rethinking every assumption about construction. The traditional model of hierarchical structure formation, the idea that galaxies grow through gradual mergers of smaller structures, suddenly seems insufficient. Maybe galaxy formation in the early universe was more dramatic than we imagined. Perhaps there were mechanisms for rapid mass accumulation that we haven't fully appreciated. Some astronomers are now proposing that supermassive black holes might play a crucial role. These cosmic monsters, millions to billions of times more massive than our Sun, are found at the centers of most large galaxies. Their formation has always been somewhat mysterious, but perhaps they appeared earlier and grew faster than we thought possible. An actively feeding supermassive black hole could enhance star formation in its host galaxy through complex feedback mechanisms, simultaneously fueling growth while regulating it through powerful outflows and jets. Others point to dark matter. We know it outweighs normal matter by a factor of 5 to 1 in the universe, and it provides the gravitational scaffolding for galaxy formation. But maybe in the early universe, dark matter halos were denser, more concentrated, and more efficient at funneling gas into star-forming regions. Perhaps the seeds of structure from the Big Bang were stronger in certain regions, creating hotspots of rapid galaxy development. There's also the possibility that star formation itself operated differently in the primordial universe. The first generations of stars formed from pristine hydrogen and helium, untainted by heavier elements. These population 3 stars, as they're called, were theoretically massive and short-lived, dying in hypernova explosions that could trigger cascades of subsequent star formation. If these early stars were more efficient at seeding new generations than our models suggest, it could explain rapid galaxy growth. But perhaps the most intriguing possibility is that we're witnessing the result of an extreme environment, a perfect storm of conditions that allowed this particular galaxy to grow at an unprecedented rate. Maybe it formed at the intersection of multiple dark matter filaments, giving it access to vast reservoirs of gas. Maybe it experienced a series of rapid mergers with smaller proto-galaxies, accumulating mass faster than typical. The spectrum of the galaxy reveals another tantalizing clue: chemical enrichment. When astronomers analyze the light from distant objects, they're looking for absorption and emission lines, spectral fingerprints of specific elements. This galaxy shows evidence of elements heavier than hydrogen and helium, what astronomers call metals: carbon, oxygen, nitrogen, elements forged only in the cores of stars and scattered through space when those stars die. The presence of these elements in significant quantities means stellar recycling has already occurred. Stars have lived and died, enriching the gas from which new stars form. This chemical evolution is supposed to take billions of years to develop to the levels observed in modern galaxies. Yet here it is, in a galaxy we're seeing as it appeared when the universe was barely out of its infancy. Every discovery in astronomy exists within a larger context, and this brilliant anomaly raises questions that extend far beyond a single galaxy. If galaxies could form this rapidly, this brilliantly, this early in cosmic history, then our census of the early universe is incomplete. James Webb has only surveyed a tiny fraction of the sky. How many more of these luminous, complex ancient galaxies are lurking in the data, waiting to be recognized? How many are hiding just beyond the current limits of our detection capabilities? The answer to that question has profound implications for our understanding of cosmic evolution. If these bright early galaxies are common, then the early universe was a far more active, energetic place than we imagined. The era of reionization, when the first stars and galaxies began producing enough ultraviolet light to ionize the hydrogen fog that filled space, might have proceeded differently than we thought. More luminous galaxies mean more ionizing radiation, potentially reionizing the universe faster and more completely. This, in turn, affects our understanding of cosmic structure formation. The temperature and ionization state of intergalactic gas influences how easily it can collapse into new galaxies. A brighter early universe means a hotter intergalactic medium, which could suppress the formation of smaller dwarf galaxies while potentially enhancing the growth of larger structures. There's also a humbling realization embedded in this discovery. The universe is more creative than our models. We build sophisticated computer simulations, incorporating our best understanding of gravity, gas dynamics, star formation, and black hole physics. We run these simulations on some of the most powerful supercomputers in the world, watching virtual universes evolve from the Big Bang to the present. Yet nature has found a way to surprise us, to exceed what we thought possible. This is both frustrating and exhilarating. Frustrating because it means our models need refinement, our assumptions need challenging, and our understanding has gaps. Exhilarating because it means there's still so much to discover, still fundamental mysteries about how the universe works waiting to be uncovered. Consider what this means for the broader question of cosmic habitability. If complex galaxies with multiple generations of stars could form this early, then the production of heavy elements, the carbon, oxygen, nitrogen, and iron necessary for planets and life, began earlier than we thought. The universe became chemically enriched faster, creating the conditions for planetary systems sooner. Does this expand the potential timescale for life in the universe? Perhaps. If Earth-like planets could form in the first billion years of cosmic history, rather than waiting several billion years, then the universe has been habitable longer than we imagined. Though, of course, the early universe was a more violent, energetic place. Active star formation, more frequent supernovae, more powerful radiation fields. Conditions that might simultaneously create the building blocks of life while making it harder for life to survive. The discovery also highlights the revolutionary power of James Webb. Every major astronomical observatory has exceeded expectations, revealing surprises that justified and then surpassed the investment in their construction. Webb is continuing this tradition, peering into cosmic epochs that were previously opaque to us, revealing the universe's early chapters with unprecedented clarity. And we're just beginning. Webb has been operating for a relatively short time. Its primary mission is expected to last 5 to 10 years, but like Hubble before it, it could continue far longer. Each deep field observation, each spectroscopic survey, each targeted study of distant galaxies promises more discoveries, more challenges to our understanding, more glimpses of the universe's hidden complexity. The story of this brilliant ancient galaxy is, in many ways, a story about the limits of human knowledge and the endless capacity for the universe to surprise us. We build our understanding of the cosmos piece by piece, observation by observation, theory by theory. We create models that explain what we've seen, that predict what we should find next. And then, inevitably, we discover something that doesn't fit, an anomaly that forces us to question, to reconsider, to expand our thinking. This galaxy, blazing across the infrared detectors of James Webb with its impossible brilliance, is one of those moments. It's a reminder that the universe is not obligated to conform to our expectations, that the early cosmos, that realm of extreme conditions and rapid change, just after the Big Bang, operated under rules we're still learning to decipher. The light from this galaxy has been traveling for nearly 13 billion years to reach us. It departed on its journey when the universe was young and wild, racing through expanding space, its wavelength stretching from visible into infrared, carrying information about that distant time and place. And when it finally arrived at James Webb's golden mirror, it told us something we weren't prepared to hear, that the infant universe was more capable than we imagined. What else is hiding in the depths of space and time? What other impossible objects are waiting to be discovered, ready to overturn our assumptions? How many more surprises does the early universe hold? These questions don't have answers yet, but they will, because that's how science progresses, not in smooth, predictable lines, but in leaps and surprises, in moments of confusion that become moments of revelation. Somewhere in the universe, nearly 13 billion light-years away, that brilliant galaxy still shines, though by now it has evolved, merged, perhaps become part of a galaxy cluster, indistinguishable from countless others. But in the light we see through James Webb, it remains forever young, forever brilliant, forever impossible. And in that impossible light, we find one of the most profound truths about the cosmos, that we are still, even after centuries of astronomical discovery, just beginning to understand the universe's true story, that the past holds secrets we're only now learning to read, that looking outward into space is also looking backward in time, toward a cosmic dawn that was brighter, stranger, and more wondrous than we dared to dream.